Hi all. For the rest of the week, we are going to be talking about ways to find the shortest path between vertices in a graph. And we are going to start with the single source shortest path problem, which is the problem of finding the shortest path from just one vertex to every other vertices in a graph. Now, this is something that you have done in Com2D5, Com2010, when you learned Dijkstra's algorithm. So I can expect that you already know how to find the shortest path. And it's something you can go for yourself if you forgot. It's easy to find resources online for it, and I also made it the submission for this week. So hopefully some of you at least have already revised this on your own if you forgot how to do it. I am going to go over it very briefly, but we really won't have any time to give it a good discussion because we're going to be looking at other algorithms which you probably haven't heard before. So this lecture here is really more about the shortest path problem in general. For example, we are going to discuss how to break down the shortest path problem into its subproblem, and we're also going to discuss about its optimal substructure. So this is going to give us a good foundation to discuss the algorithms for it, and also relevant for the next lecture when we discuss all pairs shortest path problem. That is when you try to find the shortest path between each pair of vertices simultaneously. Right, so this is actually something you can think about now. If you want to find the shortest path for each pair of vertices in the graph, you can just use Dijkstra over and over again, right? So you apply Dijkstra on one vertex, you find the shortest path to every other ones, and you apply on the second vertex, you find the shortest path to every single one again, and so on. But do you think that if you actually want to find all of them, do you think it would be faster do you think you can do it faster if you know that you're going to need all of them? Another question you can think about is, well, you know Dijkstra will just find you the shortest path from one vertex to every other vertex. If you just want to find the shortest path from one vertex to just one more vertex, it's just one other vertex. Let's say A and B. What's the shortest path between A and B? I don't care about A to C, A to D, A to E. I just want to know the shortest path from A to B. Do you think you can do it faster than Dijkstra? So this just showing you that the shortest path problem, it can be pretty deep, right? It's a very well studied problem, and it's interesting, and there's lots of algorithms related to it because it's not as simple as what you learned in Com2D5, Com2010. Okay, so that's what we're going to be doing this week. We're going to go back to shortest path problems, and yeah, hopefully you learn a thing or two. Now, notation-wise, we're going to stick to the notation that we used in the last lecture. In fact, we're going to be using this for the rest of the week, I guess, because we're going to be dealing with the shortest path for the rest of the week. So every graph that we're going to have is going to be weighted, and it's going to be directed. As before, we're going to use W to represent the weight of the edge. And something we just knew for this week, we're going to use P, UV, to represent the path between U and V. Well, the shortest path, I should say, between U and V. So the xi's are variables to represent the vertices in the shortest path, with x1 being U and xk being V. So there are k vertices in the shortest path here. Now, even though I define PUV like so, we're actually going to worry about finding the weight of the shortest path and not the path itself. Usually it's not too hard to find the path anyway, but you do have to do something extra to get it. So in most of the algorithms that we're doing, I think we're just going to be looking for the shortest path and not the actual, we're only going to be looking for the weight of the shortest path and not the actual path. Right. Okay, next up, problem decomposition. By now, you know that if you want to solve a problem, then you would have to find a way to break it down into small subproblems. And what I have here is a very basic breakdown that you can do with the shortest path problem. So if you want to find the shortest path from U to V, then you will have to go from U to other vertices. And this is what the recursion tree should look like. Starting from U, you try to go to Y1, you try to go Y2, you try to go Y3, and so on. Right? So these are all your subproblems. You're going to try to go to every single one of these vertices. Now, just a note, Sorry, just a word on the notation that we're using in case you're not sure how this x1, x2, x3 works. So if y1, y2, y3, and so on are the vertices in the graph, then, for example, I can represent the shortest path like so. Let's say the shortest path is going from u to y1 to y4 to y7 to v. So here it is. So in this case, x1 is u, x2 is y1, x3 is y4, x4 is y7, and x5 is v. Okay, so yeah, hopefully you understand how this notation works. Now, this tree here shows you the subproblems that you have to do, but that doesn't really tell you the relationship, right? Which is actually given here. If you want to find the shortest path from u to v, and you go into y1, then you have to take into account the cost of going to y1. So that's the weight of the edge u y1, and so on. And of course, don't forget that you can go directly from u to v. Well, maybe you can. If there's a path directly from u to v, then you have to consider that the weight of that edge as well, because that may actually be the shortest path. So if you think about the recursive relationship, here you have it here. Well, actually, this is probably the most important bit. Just saying that you try to go to every other vertices, y1 up to yl. But here, the other minimum here is just saying that, well, don't forget that you can also go directly from u to v. Okay, so that is a recursive relation for the shortest path problem. Now, does the shortest path problem, with that recursive relationship, does it have an optimal substructure? Alright, let's talk about this, because I noticed that some students are still struggling with the whole idea of optimal substructure. And here I am again saying that, hey, it's really not that hard. Does the shortest path problem exhibit optimal substructure property? Yes, it does. And we're going to prove it using the cut and paste argument that we have always used, which is a proof by contradiction. Suppose that PUV is the shortest path from u to v. Of course, from u, you would have to go to another vertex, say ym. And we have to solve the subproblem of finding the shortest path from ym to v, right? Now, the solution to that subproblem must be the shortest path from ym to v, because if it's not, then I can find another path between ym to v, which is shorter, and I can put that into my, well, I can just add u in front of it, so u goes to ym and it goes to v, and that will result in a path which is shorter than puv. And this is a contradiction because earlier we said that PUV is the shortest path from u to v. So this is saying that if PUV is the optimal solution, it must also contain the optimal solution to its subproblem, proving that it has the optimal substructure property. This is yet another example of showing the optimal substructure property. So you might be bored of it by now, but if you're still struggling with it, well, hopefully this helps. Or if not, we can discuss about this more in the workshop. Just go ask me during the workshop, alright? Now, CLRS does the optimal substructure slightly differently. And I actually like this more than what I had before. Basically, they're arguing if you have the shortest path from u to v, then any subpath between two vertices must also be the shortest path between them. So for example, if we have xi and xj in the shortest path, right? Then this path between xi and xj, like meaning whatever vertices are in between, they must also be the shortest path between xi and xj. Because if it's not, well, it's the same argument, right? If there is a shortest path, let's say this green lines here, then I can just substitute in that path into PUV, and I will end up with a path which is shorter than PUV. So that invalidates the fact that we say PUV is the shortest path. This is a contradiction. So again, same argument, slightly different way of looking at optimal substructure, but it's the same argument. Okay, so hopefully that convinces you that shortest path problem does have optimal substructure. And now let's move to the algorithm that you learn in Comp25, Comp 2010, to find the shortest path from one vertex to every other vertices. The algorithm is actually quite simple. You're going to start from vertex u, well, I guess we're going to start from vertex 1 in this example here, and we're going to find the distance to every other vertices. All right, so I've started from 1, and what I do is I'm just going to list all the vertices that I can reach. So I can go to 2, it'll cost me 4. I can go to 5, it'll cost me 8, and I can't go anywhere else. Now, if I want to improve the path from 1 to, well, every other vertices, then I will have to go somewhere else. And I'm just going to choose the vertex which is closest, which in this example is 2. And I'm going to add this vertex 2 in the visited set S. Now, what I'm going to do now is I'm going to look at all the edges leaving 2 to see if I can improve the shortest path from 1 to all the other vertices. Now, here I can see that I can go from 2 to 5 at a cost of 3. It cost me 8 so far to go from 1 to 5, but if I go to 2, it will cost me 4, and then from 2 to 5, it will cost me 3. So I can improve this to 7. And also from 2, I can go to 4, it will cost me 9. Whereas from when we first started out, we couldn't even get to 4. So we say infinity here. So now I can improve that to 13. So right, that's what we'll do. That becomes 13, and that becomes 7. Great, so now we're up to 2, we can't go anywhere else. Well, we're not going to improve anything else, so what we do is we just going to select the next closest vertex, which is going to be 5. So we add 5 to the set S, and from 5 I can go to 4, it'll cost me 1. So instead of 13, well, you can go to 5 at cost of 7, and from 5 you can go to 4 at cost of 1. That means you can go to 4 at a cost of 8. We're done with that. Now let's go to 4. We're going to add 4 inside the set S. And from 4, it'll cost me 5 to get to 3. So now I know that the shortest path from 1 to 3 is 13. Right? So it's just 8, the cost of me going to 4, plus 5, the cost of going from 4 to 3. So that is a very quick rundown of Dijkstra's algorithm. If you want to find the proof of correctness for Dijkstra, you can go to CLRS, page 659, 61. I'm not going to ask that in exam, but really, the correctness hinges on just one invariant. The weight of the path to the vertices in S is the shortest path to those vertices. And you can see in the textbook they prove this. They prove that the invariant is true at initialization. The maintenance one is the one that takes a while to go through, and of course the termination gives you the correctness of the algorithm. Okay, so about complexity, if you implement this naively, it's going to cost you v squared plus e. So I'm a bit lazy here, I guess. I should probably say the size of v, not actually v squared, but people do this anyway. It makes it's completely clear. So here v refers to the size of the like the number of vertices you have in the graph, and e refers to the number of edges you have in the graph. So what I mean is that I should use the order symbol, like 2 vertical lines, to signify that. But no. This is simpler to write. So why is it big O v squared plus e? Well, we have to do this algorithm few times, right? Because we have to visit every single vertex. And every time we choose the next vertex to go to, we have to find which one's closest. In a naive implementation, you would just put all the vertices in an array. So you'd have to do a linear search to find the next smallest one. That's why this is v squared, because you have to do v times, and every time you look for the smallest one, there's another v operations. When you actually improve the vertex, when you improve the distance of going from one vertex to another vertex, the complexity of that operation is actually captured in the e here. Because you think about it, every edge will only be checked once. And you check the edge to see if you can improve the distance, well, if you can improve the shortest path between 2 vertices. So really, this v squared here comes from the fact that you have to do the v times, and each time you got to look for the closest vertex, another v operation. So if you can improve this part, you can run this algorithm in, let's say, v log v plus e. If you can find the next vertex in log v time, then this will be your running time. Okay. Again, this is something we can discuss in more details during the workshop if you like, because yeah, a lecture is not very ideal because I'm not too sure if there's something you don't understand. But yeah, I'm going through this rather quickly because Dijkstra is not a COM 3010 material. You've done it before, and I'll leave it to you to revise on your own. And I'm probably not going to ask anything about Dijkstra in the exam. I don't think there's a slot for it. But I do need to mention Dijkstra because I'm going to show you that it doesn't work in some cases. In particular, when you have a negative weight in the edges, then Dijkstra will not work. All right, let's see this in action. Let's try to apply Dijkstra on this graph here with -5 in this edge and -5 in that edge there. Now, well, I'm going to start with 1. Well, I'm going to find the shortest path from 1 to every other vertices. And I can go to 5, it'll cost me 2. And I can go to 2, it'll cost me 4. So I guess the next one I visit is going to be 5. And from 5, I can go to 4, it'll cost us 6. So I'll improve this one to 8, I guess. And from here, let's go pick the next one. I'm not going to improve on 5 anymore, right? So we assume that this is the shortest path from 1 to 5. It's going to cost me 2. So I guess I'm going to pick 2 next. All right, it cost me 4 to go to 2. And from 2, can I go anywhere else? Yeah, I can go to 4. And that's pretty much it. So I can't go to 3 still. And then I guess next I will go to 4. And from 4, I can go to 3 at a cost of -5. So actually it cost me 8 minus 5 to get to 3. It'll cost me 3 to get to 3. So Dijkstra tells you that these are the shortest path from 1 to every other vertices. And hopefully you can see that this is wrong, because I can go from 1 to 5 at a cost of -1 by going 1 to 5. And it gets worse, because I can go from 1 to 5 at a cost of -1. That means I can go to 4 at a cost of 5 instead of 8. And because I can go to 4 at a cost of 5, I can go to 3 at a cost of 0. And none of that was captured in Dijkstra's algorithm. I mean, you can try to run it, but yeah, because as soon as you fix a vertex into S, you're done with that vertex. You don't try to update it again. So clearly Dijkstra will not work. But can you find the shortest path from one vertex to all the other vertices? Yeah, you can, sure. -5, minus whatever the negative numbers is just another number. There is a shortest path from 1 to 3. There is a shortest path from 1 to 4 and so on. However, let me change one edge. Let me change this edge 5, 4 from, sorry, what was it before? It was from 6 to -6. Now, let me ask you, what is the shortest path from 1 to 2? Well, it costs you 4, right? Like going like this. But wait. If you go down from 1 to 2, it'll cost you 4. If you go down to 5, it'll cost you -5. So this costs you -1 to get to 5. -6 to go to 4. So now it costs you -7 to go to 4. -5 again. It costs you -12 to go to 3. So -12 plus 7 is going to cost you -5 to get to 2. It's not 4 anymore. It's actually -5 because you just do this round trip. Right? This green arrow here, it'll tell you that it costs you -5 to get to 2. But is it actually the shortest distance from 1 to 2? Well, it costs you -5 to get to 2, but now you go back to 5 again, and you go down to 4, you go down to 3, you go down. Every time you do a cycle, you're actually reducing the shortest path by -16 plus 7. You reduce by -9. So the next time you do it, the distance from 1 to 2 is -14. Well, you can probably argue that you're not allowed to use the same edge twice. But even then, if you have a cycle where the total weight is negative, that will still give you problems with the other kind of algorithms. So what we're going to do is, we're going to say, if the graph contains negative weight, can you find the shortest path? Yes. But if there is a negatively weighted cycle in the graph, then the shortest path will not be well defined. So what we want to do, we're going to say that all the graphs that we're going to be working on, they will not contain negative weight cycles. Because again, if you have a negative weight cycle, you can just keep on repeating cycle. You will have the distance become, sorry, the path will become shorter and shorter and shorter. Well, it will become negative. Okay, so that's what we choose to do for negative weights. And I guess one more thing to talk about, cycles, because we talked about cycles. Here's a question for you. If you have the shortest path between vertex A and vertex B, well, I guess, sorry, between U and V, will there be a cycle in that shortest path? Okay, let's think about that. If the weight of the cycle is positive, so let's say U goes to xi and xi has cycle go back to xi and it goes to V. If the weight of the cycle is positive, then you remove it, you're going to end up with a shorter path, right? So the weight of the cycle cannot be positive. If the weight of the cycle is negative, then we enter the general condition that we talked about here. We're just gonna say, oh, well, we can't find the shortest path because it's not well defined. So we can't have that either. Which means that the only possibility is for the cycle to have a weight of 0. So like it's completely neutral. But then if you remove that, you get a path with the same weight. So we're going to adopt another convention. We're just going to say that the shortest path you have will not contain any cycle. Okay. Now, one more topic. Relaxation. I think this is the last one. Yeah, this is the last one. This is not really something you need to know. It's just the lingo that we're going to be using. See, the algorithms that we're going to look at when we're finding the shortest path, what we do is normally we just gonna say we're gonna start with an upper bound for the distances between two vertices. Like in Dijkstra, we say, well, from 1 I can't go to all these vertices, so I'm gonna say infinity at the start, right? And whatever we do, whatever algorithm we just do, we'll always try to use other edges to improve the distance that we have so far. This process is what we call relaxation. So relaxing an edge means that we're using that edge to see if we can find a shorter path. Maybe an example will help here. So let's say dum is the distance between u and m, and then dun is the distance between u and n. If the distance from u to m is longer, is bigger than the distance between u and n and the weight from n to m, then we can relax this edge and m to improve the shortest path from u to m. It's just a lingo that we use. Like we're saying that if we say we're relaxing nm, that means we're using nm to improve the distance from u to m, like, or whatever. That's what relaxing means. Relaxing means you take the edge and then you use that to improve the shortest path. All right, so just in case you hear the word relaxing, if in case I use the word relaxing and you have no idea what it means, that's what it means. Simply just choosing the edge, use the edge to improve the shortest path. Okay, I think that should be enough for this lecture. We're really just going through the basics of finding shortest path. And the next 3 lectures, we're just going to be seeing algorithms for finding shortest path. So make sure everything here, make sure you understand everything that was discussed in the lecture before you go to the next videos, because these are the important concepts that you need to know before you deal with the algorithms. Okay, so yep, I'll see you in the next video then.